But there was a famous physicist, Richard Feynman. So he proposed that quantum computers could exploit the properties of quantum mechanics, such as superposition and entanglement, to perform certain type of tasks that can be much faster than classical computer. So that early idea actually now becoming real. So quantum computers harnessing the principle of quantum physics to handle data and carry out computations, and introducing a different type of traditional like programming than our traditional programming language. So the core of quantum computing is qubit, which is the fundamental unit of memory. So these qubits are built using like various physical system like spin of an electron or polarization of a photon, which enable this qubit to take the advantage of quantum phenomena like superposition and entanglement, that we'll see this superposition entanglement later today. So one of the key breakthrough of quantum computing is its ability to take like complex problems that are currently beyond the capabilities of classical computer or even supercomputers. So let's see, like we are talking about qubit. So what is actually qubit? So our regular computer, we use like a lot of tiny unit of information. We all know that called bits, like either 0 or 1, which is very simple. Now, in quantum computers, we use something different, which is qubit. So the interesting thing about qubit is that it is not limited to only 0 and 1 like classical bit, and that is because of the superposition property. A qubit can exist in a blend of like both 0 and 1 at the same time. So if we think like a spinning top, if you see the example, so while it's spinning, you can't really say that it's pointing exactly at one position. It is in a mix of position, just like a qubit that can be a mix of 0 and 1 until we measure it. Or like if I give an easy example, like if you imagine you are tossing a coin, so before it lands, it's flipping through both heads and tails. So while it's in the air, it is in a state of both. So that's a great way like of how we picture superposition. So once the coin lands, we get a definite outcome, either heads or tails. Similarly, when we measure a qubit, the superposition collapses and we see either 0 or 1. But until then, it is a kind of both state at once. So that's actually the beauty of superposition. It lets like quantum computers explore many possibilities at once, something that classical computers simply can't do. Now, as I have mentioned that like the core of quantum computer is quantum bit or qubit. So unlike classical bit, qubit can represent much richer state. Now, like how do we represent this state? We use mathematical tools that describe the state of qubit, like we called it state vector. So this vector is in encode like probabilities or amplitude associated with different possible outcomes if we measure the system. So if we imagine like, if you see this example, if you imagine that a car is moving along a straight road and we want to describe the position of the car at like a particular moment. So what we do in classical system, it's like very easy, straightforward. If the car is at position 4, we just represent this with a number, for example, x is equal to 4. So the car is definitely like at position 4. This is like how classical bit works. But in quantum world, things are a little bit abstract and little more like different than classical system. We can still represent the position of the car, but now the car can be described by a quantum state vector. So often we write it as like this way x. This is called Dirac notation. So here like the vector has shown like all zeros except for one position, which is position 4. So this basically tell us that the probability of finding the car is at position 4 is 100%. So that means it is still a pure state, just expressing in a like quantum way. But here is like one point is that in quantum mechanics, the same vector format allow us to represent a superposition where the car is not just in one position, but it is spread across multiple positions with different amplitudes. Now, in a classical system, as like a bit can be only in two possible states, like either 0 or 1. We can write it is like x is equal to 0 or x is equal to 1. But in quantum computing, we use Dirac notation or bracket notation to write this state. So we work in a vector space in quantum mechanics that we represent the two basic qubit states, the quantum equivalents of 0 or 1. Those are orthogonal vectors. And these two vectors are not just orthogonal, they can be orthonormal, which is like they can perpendicular to each other and they have unit length like together, like 0 and 1 from a complete basis for the qubit state. That is a two-dimensional complex vector. Because state 0 and state 1 form a basis, we can represent any qubit as a linear like combination or what we call a superposition of these two vectors. For example, if we see this, like if we there is a complex state like Q0, so like if we rewrite this state, so even though the qubit is not in purely 0 or 1, it is a valid and complete description of a qubit. This one is just a superposition. In quantum computing, a qubit doesn't need to choose between 0 and 1 until we measure it. So before that, it can exist in both in a way that enable the entirely like new form of computation. Now, let's talk about measurement. So one of the most like important or unique aspect of quantum computing. So when we measure a quantum system, we collapse the state vector into one of its basis states. So how do you actually calculate the probability of that outcome? So there is a simple rule. So look like, for example, to find the probability of measuring a quantum state, for example, like this state, if we consider this state into X, so we compute it's like this is called a Born rule, which is fundamental in quantum theory. So to understand, like there is a column vector that called kets, and there is a row vector that called bra. So if we convert like from a ket to a bra by taking the conjugate response, we see these things. Like if you see how we represent this, so this is the inner product of the vector. Then we take the square magnitude of this vector to get the probability of our measurement. So we'll see more here. Like if we apply this to an example, so if we want to know like what is the probability of measuring qubit in state 0, so we take the inner product and we know that like the 0 0 is 1 and 0 1 is 0. So if we simplify it, it becomes like this 1 by root 2 or 1 by root 2. And then if we take the square, we get half, which is like 50% the probability of measuring qubit in state 0. So in quantum mechanics, the total probability always needs to add up to 1. That means like your if we represent this way, it will the total probability will always be equal to 1. So if we rewrite this equation, so we will get the sum of probabilities for all possible outcome is 1. So measurement is basically exactly like how we extract information from a quantum system. So which plays a key role in like quantum algorithm, quantum error correction, because after if we build any circuit or if we want to get the outcome at the end, we need to measure the system. Now we have just learned how to compute the probability of measuring a quantum state. Now, if we want to take a closer look at what actually happened to the state when we perform measurements, so this is actually another like principle which is called observer effect. For example, like imagine that we have a qubit in this state, like, and this qubit is in a superposition of the basis state 0 and 1 with amplitude alpha and beta respectively. So in vector form, it looks like this. So if we, from this point, like if we perform any measurement of the qubit, it will definitely return 0 state with 100% probability. So when we measure the system, the original superposition is gone, which it replaced with a well-defined classical state. So this collapse is fundamentally affect our quantum computation. So if we measure we were about to measure our qubit constantly throughout a quantum algorithm, we would destroy all the quantum features like interference, entanglement that gives quantum computing its power. Or like if I say in other words, like if we keep measuring, we reduce our quantum system to a classical system. That's why in practice, we avoid measurement until the very end of a quantum circuit when we actually need the result. Now let's talk about like one of the visual tools in quantum computing, which is Bloch sphere. So here, like in Bloch sphere, any point on the surface of the sphere represent a possible state of a qubit. So we describe this using some angle like theta and phi. So theta represent how much weight the qubit has in zero state versus one state direction, and phi is determines the relative phase between them. For example, the top of this sphere is purely zero state and bottom is purely one state, and the points around the equator represent the equal superposition. Now, let's see some gates. So in classical computing, we all know that we have logic gates like, sorry, like NOT gate, AND gate, OR gate. So this in classical like computing, these gate take binary inputs and produce outputs. Like they are not reversible. But in quantum computing, all operation must be reversible, and they are represented by unitary matrices. So like these gates, these are Pauli gates like X gate, Y gate, Z gate. So these gates rotate the qubits state on the Bloch sphere, which gives us a like a geometric way to understand like quantum logic. So if we see X gate, it's like a classical not gate, but it flips the qubit. This means if your qubit is in state 0, if we apply X gate, it gives state 1 and vice versa. So this gate swaps the amplitude of 0 and 1. To apply this gate to a qubit, we perform matrix vector multiplication. So on the Bloch sphere, the X gate rotates the qubit by 180 degree around the x-axis. So we'll see this how to build this gate in a short while in Jupyter Notebook. And similarly, like if we look at the Y gate, it's actually it's a bit different than X gate. This gate also swap between zero state and one state, but it introduces like I'm sorry, it introduces a complex phase. If you can see the complex phase I, so you will see like this this type of gate come into play like in interference and phase sensitive algorithms. And on the Bloch sphere, this is a like 180 degree rotation around Y axis. And if we see the Z gate, so it's actually doesn't swap the gate, but instead it like flips the sign of amplitude. So if we have if we apply Z gate on zero state, we will get like maybe -1. Like that is the flip of the like the sign of the amplitude. All right, so it's like this maybe these gates look quite similar or looks the same, but if we measure it, there will be a phase shift, which is important in quantum interference. So these gates are from the Pauli family, and we always need this type of X, Y, Z gate when will build a quantum circuit. Now, there are actually single qubit gate and multi-qubit gate in quantum computing. So, a qubit in quantum computing, a qubit can be expressed in different bases, like depending on which axis we want to measure, X, Y, Z on the Bloch sphere. So, Z actually is the computational basis and the most familiar one, which is the standard gate. So there are two states, 0 and 1, and this correspond to like north and south pole of the Bloch sphere. So I was showing the Bloch sphere earlier. And okay, so we'll see like basically these are all almost similar that I was explaining like X, Y, Z gate. So we will implement this type of gate. So I think it will be more clear when we will implement after like looking at Hadamard gate. So let's see which this is actually one of the important gate because we in quantum computing we always talk about superposition. So this gate H gate is a gate that we use to build superposition. It is like superposition is a phenomena that we would like to always most of the time apply when we build quantum circuits so that it can give us like lot of more opportunities to explore like possibly many possibilities parallelly. So, so here you can see if we apply this is the matrix of H gate. So and if we apply H gate to zero state, we get a vector like 1 by root 2 1 1 if you say, which is the mathematical expression of quantum state plus. So which is like the plus state, and it means the qubit is equally in 0 and 1. With like equal amplitude, but there is no phase difference. So that will be the result of applying Hadamard gate. So if we apply Hadamard gate, if we have we have two qubit like 0 1, both qubit, we will have the equal chance of getting the probability like 50% chance of getting 0 and 50% chance of getting 1. That I was saying earlier. Like if we think about flipping a coin, it's in the air, it's spinning, and it's not settled on head or tails. But when so this is actually foundational gate of for all algorithm because it enables like parallel computation. But when we measure it, we will get a definite outcome. So there are some more gates that we apply, but actually all of these gates are basically like from polyfamily that we already explained, X, Y, Z gate. But yeah, when we apply some this type of gate, RX gate, RY, RZ gate, when we think about some applications like in quantum machine learning on quantum variation and algorithm. So here you can see like RX gate, RY gate, RZ gate. So RX is basically the rotation around x-axis. So this gate rotate the qubit around the x-axis on the Bloch sphere by angle theta. So you can see like sine and cosine. So these terms define how much of the state is mixed between 0 and 1. And that I minus I indicates this is a unitary complex rotation. So on the Bloch sphere, it moves qubit forward and backward between state 0 and state 1 through a YZ plane. All right, so if we talk about Y gate, so this gate rotate qubit around Y axis. So the same like as we are saying, like X gate rotate qubit around X axis, so Y gate rotate qubit around Y axis, but it changes the balance between 0 and 1 state without introducing a complex phase. And this is actually useful when we want to create some like real value superposition, not like the complex number. And yeah, if we look at our Z gate, that it rotates the qubit around Z axis, and this doesn't change the probability of measuring 0 and 1, but it changes the relative phase. Like the diagonal elements e to the power I theta by 2 or minus I theta by 2 are complex numbers with magnitude 1. So this acts like rotating arrows on the complex plane. Now, actually, we are talking about this type of rotation gate. So as like I was saying, like why actually we need these gates. So to prepare any qubit state, we often apply like sequence of this type of gate, like RZ, RY, RX. And this lets us reach any point on the Bloch sphere. In quantum machine learning, quantum variation and algorithm, quantum simulation, we use this type of gate to build our circuit because if you see that there is theta, this theta is tunable. So you can choose the parameter of theta and you can tune it during your optimization or building your quantum machine learning model, just like weights in neural network. Sorry, I have a little bit of cold, so sore throat. I think like I will maybe now show some of the code. Any questions so far?
So we don't have any questions in the chat yet, but would anybody like to ask any questions
Sorry.
about what we've been talking about so far in terms of qubits, superposition, those different gates that we were shown, and then the vector and matrix representations of those? Any questions about any of that content so far? Okay, I can see Lachlan, you've got your hand up. Are you happy to go ahead?
Yeah. I'm just wondering, for your Bloch sphere, I understand the concept, but what's like in the Z direction, you're describing how much a qubit is either 0 or 1. What is the kind of function of introducing that complex number? Like you've got on the X and Y plane, you actually introduce that complex number. What does that represent in terms of the actual computing and the state of that qubit? I'm just not following that intuitively, which is to be expected probably.
Okay, so I think it should be more clear, like if I run and show you some on the blogosphere. Okay, if I go to the code and
Yeah,
see.
no worries.
Yeah.
Can I say thanks, Lachlan?
Okay.
That's a great question.
Yeah.
And I've got to admit, I don't feel like I fully know the answer, so I'm really glad you asked. My understanding is it's something like phase. Is that right, Amina? Or
Yeah, yeah, exactly.
not that I really know what phase means, but I'm sure that we're about to find out. So,
Yeah, because in some of the applications, actually, for some of the application, when we build circuit, when we need like amplitude, sometimes we only need real number. Sometimes we need to change the phase. So at that time, this type of gates are very useful, like to change and see like how qubit is rotating on the Blocksphere, and which is like for certain type of applications or certain type of problems, we just need to switch between gears and see if we are getting like how we are getting it affect performance.
and just to
Maybe
check, does phase change how one qubit interferes with another qubit? If you have two different qubits, is that when you start to have phase really important? Or
no, actually no. If that we were saying that one qubit change, another qubit, that is actually entanglement that we'll go through. That like exactly like if you change one qubit, how it affects another qubit. But now we are talking about if we like zero qubit, we are talking like independently how qubits are working. But how one qubit affect another qubit, that's actually a different property in quantum computing, which is entanglement or Bell state. We'll see that.
okay.
And
Okay,
just another
actually,
quick question as well, which is the Bloch sphere is a unit sphere, yeah? Like the yeah,
yeah,
cool.
yeah,
Just double checking, thanks.
yeah. All right, so I will actually show in Jupyter Notebook instead of running in IBM because we don't have that much time and it's quite easy to show. And maybe I'll also share this with you guys because there are a lot of things, but I'll only go a little bit of it, just the main. But can you see the code?
We can, but it's a little bit small. Do you think that you might be
Uh,
able to like zoom in like just a little
right,
bit?
let me see. Is it better now?
Yeah, that's better. Thank you.
All right, so this is I actually run already this because if we would like to now install, it will take a bit of time. So you can, I think we all have Gmail accounts. So if you easily just go to Colab, you can run this type of like circuit and play. So what actually I was doing, I was installing Qiskit first, so that I have done already. Because maybe most of you know about Qiskit. We use Qiskit for building any like quantum circuit, and we use PennyLane when we are basically we are using PennyLane for quantum machine learning. But for quantum computing, there are a lot of like tutorials, a lot of documentation in Qiskit if you go to their website. So I actually installed all the libraries, everything we need to show this. Just install Qiskit, Matplotlib. Then how for some plotting, like I installed that like visualization thing. And then as we already installed Qiskit, now we are actually importing the module from there, like quantum circuit, like sparse poly, to see the observable. This is a simulator because we are not using the real quantum computer, and some other module for transpilation. So I didn't run it. So let's see. Now, actually, we are talking about the gates. So I will see that poly X gate. So initially, I'm actually defining a simulator. And defining a state vector, which actually led the simulator to store the quantum state vector. And then this is only for, only for visualization. So let me run this code. And basically, my main intention is to show you simply like how we can build a quantum circuit. So if you see this line here, like I'm only taking one qubit. So we are calling quantum circuit and taking one qubit. And then we are like saving it as a state vector. Now, as we are taking only one qubit, and if we plot it, like there is no gate yet, only one qubit. So if we plot it, where is it in the plotosphere? Okay, so you can see that like when we plot it, the qubit is certainly is at state 0. Now, if we apply some gates, how we can apply gate? Every time actually I'm taking defining quantum circuit again so that it will not affect the result from previous run. So we talk about X, Y, Z gate. So here I'm actually applying X gate in this quantum circuit. So if we draw this, so this will be our circuit. You can see like this is the circuit. Now we would like to see, if you remember previously, the qubit was in state 0 and we are applying X gate. So where the qubit should go, it should flip, right? So we are using the same function every time so that it will be very easy to understand. Like we are defining a state vector. We are using all this like simulation.run, result, state vector, get state vector to see the output and run the circuit and execution. And this plot is for plotting the state. So as we apply X gate, our expectation is that the qubit will flip from 0 to 1. So here, like previous slide answered, the output is still there. So you can see like after applying X gate, so it was qubit was in 0 state, but now it flipped to 1 state. And similarly, like if we want to build a more bigger circuit, for example, if you would like to apply Y gate or Z gate, you can easily like see like how we can build the circuit. Just you define your circuit and then apply gate. And if you want to draw. Otherwise, it's just for seeing like how the circuit look like, but you can measure the circuit. So is there any question?
Yeah, sorry to interrupt, Amina. I just wanted to quickly ask if it would be possible for us to share this notebook maybe in the chat or a copy of it, so that way people are able to work on it and like look around a bit themselves. We just had a student ask in the chat, and I thought that might be a great idea.
Sure. Yeah, I just sent you one tutorial. Maybe there's another one, but maybe I'll do it later because it's taking a bit time.
Yeah, of course.
Sure.
Just the one that we're maybe looking at together now. Does that say?
Yeah.
For notebooks, the file size can be quite large, especially if the outputs haven't all been cleared, which can make it very hard to send. So, but I assume that we don't have the time to go through clear all the outputs now. So
actually, we will upload it so like you guys can try or run all the codes at home, and feel free to send email like if you have any question, or if anyone wants to talk, I can arrange a quick meeting.
All right, thank you.
Okay, let me share again as we don't have much time. Can you see the notebook again? I'll just go through a few things.
Yes, we can see it. Thank you.
Okay, sure. Okay, so you can see like you can do like building blocks, like if you would like to add more gates, not only X, like X, Y, Z, but the basic thing is how you are defining your quantum circuit. And then you apply gate, you can perform measurement, you can draw the circuit, you can see the visualization. I think you will have this course, so it would be easier to see. All right, so as we have already seen that there is now we can apply like there is a code to apply Z gate the similar way. So let's see if I have the output here. So I didn't plot the blotch is fair, only like if we are printing the output. So here like when we apply Z gate, the result is still like 0 and is 1024 because Z only change the phase, not the probability. So previously when we were applying X gate, we see it's 1 and in total short is 1024. Now that that flipped to like 0 and it's like this with the same number of short. And when we apply like Y gate, we see the same output as X gate because Y actually flips like 0 state to high complex now one state with a like complex number, but there is no global phase that is affecting the measurement. So the result is still showing the same. But even though like there is a complex phase is introduced, the measurement probability is like still 100% for state 1. Now we have seen H gate, which I was saying, like I will say this is one of the most important gate, like interesting thing to see, which actually we can create superposition if we use H gate, which is Hadamard gate. So you can see like now I'm taking one qubit circuit, that the same thing exactly happening. exactly we were doing earlier. And previously we were applying X gate, Z gate, Y gate, but now we are applying H gate. And this time actually we will measure the qubit and see the output. So this function is to draw the circuit. So if we draw the circuit, you see like this is the qubit and this is Hadamard gate and this is the symbol of measurement. So what happened actually when we measure the system? But because we were saying that like by applying H gate, we can create superposition. That means like state 0 and state 1, we will get roughly like 50% chance of getting both states. So we would like to see the effect now. So to see the effect, we need to measure the circuit. So here is actually how we can measure, like this is you define your circuit here in QC, and if we use like measure which qubit you need to define, then you can see the measurement result. So let's see, like if we apply Hadamard gate on qubit, what happened? All right, so this is just to see the plot. So here is actually when we measuring the results for 1024 shots. We can see that here like roughly like it's almost the same 50% chance of getting state 0 and 50% chance of getting state 1, but there is a small, like you can see that there is a small difference. That is because we are not running mass shots. If we increase the shot, it will be more close to 50% chance of getting both states. So which is like now these states are in superposition. And you can simply see like if we don't use Hadamard gate, what happened? Like we use Hadamard gate to create superposition, but if we don't use Hadamard gate, then if we run the circuit, there is no Hadamard gate. We are directly removing that Hadamard gate and measuring the qubit for our circuit. So what happened then? Like we will previously when you using superposition, you were getting 50% chance of getting both states, but now there is like you can see like the whole state is 0. So the histogram is showing us for all the counts, like for 1024, it's like counts of 0 and counts of 1. It is like measurement is deterministic when the qubit is not in superposition. I think that's all. There are more things, but I will not show these things. Maybe you can explore the notebook, but we will go back to our slide now. Is there error in result 50/50 because the noise? Yeah, that's like because like when you measure the system, there is noise and error. So that's why it's not exactly 50%, 50%. Slide. Can you see the slide again?
Yep, we can see the slides. And just to double check on Kieran's question, so do we mean that there's noise in terms of statistical noise if you make a whole bunch of measurements of a 50/50 that you never quite get 50/50, but you get something close? Or do you mean like noise as in quantum noise, as in there's something that's actually messing with our qubits in the simulation that's preventing us from getting the 50/50?
Yeah, there is a little bit of like noise coming, but there will be much more noise when we will actually do on real quantum hardware. And there will be, we need some noise mitigation technique. But yeah, there is still like statistical error is coming still in the simulator. But if we increase the shot, maybe we can reduce the noise for the simulator, but not for the like real hardware. For real hardware, you need some error mitigation.
Okay, thank you.
Okay, sure. All right, so I'm moving now because I don't think I have a lot of things to cover still. All right, so we actually, so far we talked about single qubits, so how they exist in superposition of 0, 1, but quantum computing actually gets more powerful when we start combining multiple qubits. For example, in classical computer, 2 qubit can be one of 4 possible configuration, right? Like 0, 1, 0, 0, 1, 0, 1, 1, but only one of those at a time. But quantum qubits are different. If we take 2 qubits, the total system can be a superposition of all 4 combination at once. That means we can represent all 4 classical states at the same time, but with different complex amplitude. Now, why actually do we need is this important? Because quantum computers can hold all 2 to the power n possibilities simultaneously. So it can perform operations on all those combinations in parallel, which is a phenomena that is called quantum parallelism. For example, like it's from one of my experience, like one of my experimental data, like for image generation for a very simple digit, for is like 0 and 1. If we want to generate synthetic images on a classical computer, it needs like 2,500 parameters, but in quantum computer, it only took like 100 parameters. So we can see like how much reduction is in it. It's because of this, like because quantum can hold like all those possibilities at the same time, like simultaneously. Now, this is actually one of the very important gate in building quantum circuit, which is C0 gate. So in C0 gate, if like 2 qubit plays a role, like if you have a C0 gate flips the target qubit. For example, if you have 2 qubit, Q0, Q1, if Q1 is the target qubit, so a C0 gate flip the target qubit only if the control qubit is in state 0. Otherwise, nothing happens. So the C0 gate is like represented by a 4x4 matrix acting on a 2 qubit system. So it's we represent it using a dot and like plus symbol. So that's actually how we represent a CNOT gate. So if we apply, we have already seen Hadamard gate. So if we apply CNOT gate with Hadamard, there's like entanglement happen that I'll show in the next slide. There are actually some other gates if we go in more advanced thing, but CZ gate is almost like C0 gate, but what does it do actually? If the control qubit is in state 1, it applies phase flip on the target. And if the control qubit is in state 0, nothing happens. So the Z gate does not flip like 0 or 1, but it adds a phase of -1 to state 1. And there is another gate here, like swap gate. So this gate simply swap the state of 2 qubits. For example, if qubit 0, Q0 or qubit first qubit is 0 and qubit 1, Q1 is in state 1. So after, when you apply swap gate, Q0 becomes 1 and Q1 becomes 0. So it's like of information exchange between 2 qubits. So in real world, like swap gate needs to bring like basically use swap gate to bring like qubit next to each other for like interaction on real quantum hardware. So there is like another advanced gate, which is CRX gate. So it is a controlled RX gate. So it means like C stands for control and RX is the rotation around x-axis, where like there is the rotation angle theta, which is a tunable parameter. So, but most of the time for applications in quantum machine learning or variational quantum algorithm, we basically use like C0 or CZ type of gate and RY/RX gate with like trainable parameter theta. Now, there is a very important, or I will say, the heart of quantum computing. One of the most powerful concept is entanglement. So entanglement means that like 2 qubits become deeply linked. That the state of one qubit immediately affect the state of another qubit, even no matter how far they are apart. So this is actually what Einstein called it spooky action at a distance. So how we can actually create entanglement. So if we start with 2 qubit, and if we apply Hadamard gate to the first qubit, what happened? We already applied Hadamard gate, right? So when we apply Hadamard gate, we saw in the code, like it's only superposition. There is no an entanglement yet. But how can we create entanglement? So if we apply C0, so if the control qubit, if we remember C0 rule, if the control qubit is state 1, it flips the target qubit. And if control qubit is in state 0, nothing happens. So thus, and when we apply this C0 with after Hadamard gate on target qubit, that is actually the final entangled state, which is also called Veil state. So that means like you will get 50% probability of getting 0, 0, 50% probability of getting 1, 1. And there is no chance when 2 qubits are entangled, we will get either 0, 1 or 1, 0. Actually, there is, I wanted to show these circuits, but yeah, as I couldn't upload the second part, so that is actually in another notebook code. So, but if we go there, there is like circuit. So you can see that there are two qubits. I'm applying Hadamard gate and CNOT gate, and then measuring both qubits. So the code is there. I will upload it. So run this code and see like how it creates entanglement. So it will give you roughly this type of result. Like previously we have seen in superposition, we are only getting like 0, 1, like probability of getting 0, 1. But when the qubits are entangled, you will get the probability of getting 0, 0, 1, 1, but you will not get any like 0% chance of like measuring 0, 1 and 1, 0. So I was actually keeping some of the task for you. So please try this task at home and yeah, get back to me if you have any questions. Just a very simple thing like create superposition with Hadamard gate and what are you observing, and then create entanglement and see your observe what you are observing or you are understanding when you are running on simulator. But this, like all of the gates I already described, I explained, like for creating superposition, you need Hadamard gate that we have already seen. If you want to create Bell state or entanglement, you can take two qubit, you apply Hadamard gate on qubit 0 and you apply C naught and measure both qubits and see, like plot, like what you are watching. All right, so actually that are the fundamental thing I wanted to explain today. But now I will actually give a bit of idea that what we are doing in CSIRO in quantum sector. So there are basically four area in CSIRO is working: quantum sensing, quantum communications, quantum computing, and quantum energy. And this is quantum computing is basically my area of research. And in quantum computing, our leading applications are in medicine and healthcare, in defense and military applications, in quantum chemistry, decarbonization, in transport and logistics. And these are actually these three sectors basically I work on. So let me show some of my recent work. So this is actually a quantum classical hybrid transfer learning approach. So you might not know like what is quantum machine learning. So I basically work on quantum machine learning. So quantum machine learning is, I'll say, like very interesting, cutting edge, rapidly evolving field where quantum computing meets AI. So at its core, like it's about getting or leveraging the unique principle of quantum mechanics like superposition entanglement to enhance the capabilities of machine learning models. We know like nowadays machine learning is everywhere. It's rapidly like becoming like very interesting, and the integration in real world application is already addressing high complex challenges like in early disease detection, in medical imaging, anomaly detection, in natural language processing for chatbot, for image recognition. But when machine learning is getting very like in everywhere, the demand of computational power and efficiency also grows. And that actually leads like researchers to investigate quantum machine learning, if quantum can help in machine learning, to accelerate machine learning task by using, because we know like in computational demand or in robustness. So the application of quantum machine learning to large scale high resolution image data set is not yet possible because of like, because it needs a lot of qubit, but we have a limited number of qubit in quantum hardware, and there are relatively high level of noise in the current generation of quantum device. So in this work, we have developed a quantum transfer learning approach that integrates quantum variational circuit with a classical machine learning framework. So this approach is like highly relevant to real world application, multiple real world application, like where data is complex and high dimensional, but quantum hardware is limited. So when I was like discussing some of the gates like RX, RY, RZ, Hadamard gate, you can see like we used all those type of gate actually to build a like quantum machine learning model and build a variational quantum circuit. So in like quantum machine learning, there are basically some three, I would say like three standard stage. Like your data is classical, but your system is quantum. So you first need to encode your data into quantum state. Then there needs to be a circuit where you will have trainable parameters, and at the end you will measure your circuit. So those are basically the three three standard stage of quantum computing. And in this work, we actually outperform classical transfer learning for high dimensional data. But as like we develop quantum machine learning models, so at the same time, we would like to ensure that our model is vulnerable against adversarial attacks. So if we don't know adversarial attacks, adversarial attacks are like, like optical illusion for AI. If there is tiny intentional tweak we can make or attacker can make in the input data, it can make the model make mistakes. For example, if there is a self-driving car and it might misinterpret a pedestrian as a shadow. So those are life-threatening challenges, right? So we actually, in our earlier work, we investigate that the effect of those type of attack in classical machine learning. And you can see like for some standard attack like PGD, FGSM, auto attack, how classical machine learning results are dropping against those type of attack. Like it was 80%, but only with a small attack, now the model is misinterpreting is like, it's like going to 0%. Now, as we develop quantum machine learning model, our main question is quantum machine learning can be tricked like classical machine learning? So we have seen in one of our study that if you see this curve, these are quantum machine learning. These are the results for quantum machine learning models, while this is for classical machine learning. So you can see like how quantum machine learning is more resilient against this type of attack than classical machine learning, and which is actually, I'll say, most like one of the very interesting and most near-term applications that quantum machine learning is more provide more resiliency against this type of data manipulation attack. But like here, like this type of attack actually from the attack is generated for a classical model, and then we transfer it for a quantum model. But what happened, like if the attack is generated for a quantum model and we are testing for quantum model, I mean for white box attack. So we actually, in one of our another work, we investigate that the white box and black box attack. And in both cases, actually, we generate the attack for quantum model and also test for a quantum model to see like how attack is, how model is performing in white box scenario, while the attacker already have the information of your model, your hardware. And in both cases, our quantum machine learning model like also failed to um, protect the system against this type of attack. And then we came up with the idea of like introducing a quantum machine learning framework and demonstrate its robustness, because we are bringing an encoder decoder that can purify the attack images. So the attack image will not receive, will even not reach to your quantum machine learning model. So actually this type of work we are doing in our quantum system team for quantum machine learning. And there's like, I'm not going into any details because of time, but we also work in healthcare. And you can see like those type of gate I was describing, like we use those type of gate to build a quantum machine learning model. And actually this is actually generating synthetic images in healthcare domain. So we worked with MITRE and Cleveland Clinic USA for this project. And the interesting thing I just want to mention is that if you look at the parameters, these are the parameters you can see for classical machine learning model, while it is only very much less than classical machine learning model compared to quantum machine learning model, which is only around 3,000 parameters. So this is actually very interesting because we can have the application in disease diagnosis, in patient outcome prediction, like drug discovery. But yeah, we are talking a lot about quantum computing, quantum machine learning model. There are some possibility that for some computationally intensive problem, where like we need a vast amount of processing power that classical computers struggle with, or even like a supercomputer struggle to find a solution, quantum computer has the potential like to provide significant speed up, reduce the computational resources. But at the same time, when we are seeing a lot of possibilities, there are some, we need to be realistic. Like quantum computing is powerful, but it's not easy. There are a lot of challenges like that researchers are heavily working. So one of the first challenge I would say is coherence time, or in simple terms, like how long a quantum state can survive before it collapses. Because the qubit is very delicate. It interacts with environment like heat, light, or vibration and quickly loses its quantum properties. And there are other challenges like error rate and noise are a huge problem. In classical computers, we might have a like one error in a billion of like operations. But in quantum computers, errors happen all the time because the system is so sensitive. Even every time we apply a gate, we measure a qubit or even just wait, noise can corrupt the information. So an important thing is when noise causes wrong rotation, unintended flips, and we lost information. And like, but there is coming like quantum error correction. In researchers are heavily working on quantum error corrections to mitigate this type of noise or error in a system. And another thing is scalability. Like we nowadays we are building a lot of quantum algorithms, but all most of these are for a very like small scale or toy size problem. So scalability is another challenge that researchers are working to address. So yeah, so like there is a lot of opportunities, but lot of potentiality, but there are a lot of challenges. But yeah, research is going on. So yeah, we are heavily the research is going on. So maybe like in next few years, 5 or 10 years, we could design a quantum algorithm that can solve certain type of classical problem much better or faster or provide more resiliency than classical computing system. I think that's all from my side today. I was putting a slide for Akib. Yeah,
Thank you, Amina. Thank you.
I'm not sure if Akib is here already or.
I haven't seen him yet.
He is here. Yeah, no, I can see
Oh,
him.
he's here. There you are. Sorry, you were hiding out in there. Hello, Akib.
Hello.
So my understanding is that you might need to leave us now. Is that right?
Yeah, I will leave now, and Akib will continue. And Akib is also we are from the same team. It should be fine.
Yep. So I can see that there are a couple of questions in the chat from Kieran.
Yeah.
Do you have enough time to look at those before you leave, or should we leave that to Akib to answer those questions?
No, that's fine. It's quantum machine learning. So does quantum machine learning require less data than its classical counterpart? No, it's not about less data. The data will be same, but there will be a very less number of parameters in quantum computing compared to classical computing, but data would be the same, but we just can't use the classical data directly into our quantum system. We need to encode the data in a way that quantum computer can understand. I don't see any other, I think 50-50 chance. I think that's answered the question, but if
and
there
then,
yeah.
There was also the one about I think you clarified this when you were speaking before, but yes, quantum machine learning has less parameters to learn or to fine tune.
Yes.
And
how does lesser parameter improve efficiency? I will not say it's improving efficiency, but in real quantum hardware, maybe like it will take much, it will be much speeder or much faster, but I will not say that it is affecting or it is improving the efficiency. Even I will not say that quantum machine learning is outperforming classical machine learning, but there could be potentiality for certain type of applications. And as I have shown, like one of the most interesting or near-term application is quantum machine learning is much more robust against very very serious security type of applications than for like data manipulation attack. But so far, I will not say like we are outperforming classical machine learning.
Thank you. Thank you.
Thank you, everyone, and thank you. So maybe if you have any question, feel free to send email. Yeah.
Okay. We will. And we will get that notebook available for the students as well. Thank you so much, Amina. Bye. Thank you.
I will send you the second notebook as well, because there is a entanglement that everyone can explore.
Okay, that would be great.
Okay, bye, everyone. Thank you so much for joining.
And now we have Dr. Akib Karim. Did I pronounce that correctly?
Yeah, that's it.
Excellent, thank you. Who's also a research scientist at the CSIRO, and working in quantum systems. And his background is in quantum chemistry, and now he specializes in quantum algorithm development, in particular with applications to quantum chemistry, solid state physics, which in my opinion is kind of like another word for chemistry, or it's the chemical side of physics, and machine learning. So with that, I might pass over to you, Arcube, to take us through things, and then if, I'll be able to monitor the chat, and if you need any help with anything like distributing links or anything like that to the students, let me know. The other thing that if you would like, we could have a quick break now, like a 5-minute break or something like this, because I know that we've been here for a bit more than an hour already. And so, yeah, the students may want to break. I'll let you decide about that.
Yeah, I think a 5-minute break would be okay.
Okay, so in that case, we'll take a 5-minute break. So by my clock, we're at 10:38 right now. So maybe, shall we just say if everybody's back, we're going to start at 1:45. Does that sound good? So we'd recommend getting back slightly before 1:45, the hour. So that way we're going to start right then. Does that sound good, Akib?
Yep.
All right, so see everybody a minute before 1:45. All right, I think it's probably time to start coming back now. So if everyone, I mean, most people didn't have their camera on before, and you don't have to have your camera on. So I'm not expecting you to necessarily turn your camera on to let us know you're back, but maybe if you just want to post in the chat something like ready to go or something like that, and then we can get started. So Angus, you've got a question? Or you're putting up your hand up to let us know that you're there. Got it. That makes sense, probably. Yep. All right. I think I saw somebody do a reaction as well. So thank you very much for that. And we got people in the chat saying they're ready to go. So then, Cube, are you happy to kick us off? Well, we're not starting before Akib gets back, that's for sure. So let's just wait here a quick minute and just see. What I might try to do preemptively before he gets back is there is a notebook that that Akib has asked to be shared, and so what I might do is I'm just going to quickly put that in the chat for you, and I might give you some instructions for how to use it. So that way it's all ready to go when Akib gets back. So I'm just putting in the chat now a link. Hopefully this works. So if you go to that link, it should look a little bit like this. I'll just quickly share my screen to show that to you. So this works. So I'm just sharing my screen on the right-hand side, or just over here. And can you guys see how there's this button that says copy to drive? So if you have a Google account, then you should be able to make a copy of this notebook for yourself and use it, okay? So, yes, so I'd like to, just say that is a way that you can use this notebook for today. And with that, I think I'll stop sharing because I think, Akib, you're ready to go now. Is that right?
Yep.
Excellent. Hopefully it was the right thing for me to do to share that notebook with everyone.
No, that was brilliant. That's fantastic. Yeah, thank you. Thanks
Excellent.
so much. Yeah.
All right, I'll pass over to you.
Yep. So I'll do a little bit of talking first, and then, because last year I had like a whole slides and I was talking the whole time. I thought this year might be fun. I built this sort of little toy that we can play around with. And that might make it a bit more like you can get a better feeling for this topic that I will introduce. So
that sounds good. Thank you.
Yeah. I'll do full screen. And I'll do.
Come on.
Let me know. Does this? Well, oh, that has died on my end. Present. Does this look okay?
So basically, we can see the first slide of the PDF at the moment. Is that
Okay?
good?
Great. Yep, that's fine.
Perfect.
Yep. Okay. So I believe that Amina has talked you through sort of what the concept of a quantum computer is, and some of the ways that we like start with the concept of like a qubit, how it's representative of quantum data, and we can manipulate it using gates, and we can do stuff like run algorithms, like quantum machine learning, and sort of the way we conceptualize of a quantum computer in a way that we can show how it's useful and actually use it. But today I'm going to talk to you about like when we actually want to build a quantum computer, like what is it? What is the thing that's going to be sitting in your lab? What is the thing that's going to be actually running this abstract concept of a quantum computer? So I guess my first question is, does anybody know what this picture is that I've put up on the title slide? And I guess I can't really see the chat, so if somebody said something.
That's okay. I'm monitoring the chat. I think people are going to need a little bit more time than that to be able to answer the question.
Fine.
Kieran said it's a quantum computer, and I think I would agree with that. But I'm wondering if you want us to be more specific. Ooh, here we go. Somebody's called it a dilution fridge or a fridge. So it's a way of making a quantum computer really cold, maybe? Ooh, superconducting has been said as well.
Okay, yeah.
And
So
somebody's
this is
pointed out that it's beautiful.
I'm glad you think that.
Like a chandelier.
Yeah, they do call it that. Yeah. But yeah, so it is a dilution fridge. So this is basically like in the lab, it's in a little metal cylinder. So it does look like a giant, like unlabeled can of like a soft drink or something. But inside it does look like this. It's a fridge. At the very bottom, there would be like maybe a little chip that would be like contain the qubits and do the whole quantum computing thing. But typically, you know, the image that we give it is like this thing, which is just a fridge. The whole setup is just to keep it cold. So what I'm hoping is for these lectures, we're just going to like elucidate a little bit about exactly what's going on. And I'll give you some examples. So first, I think there was already an introduction, but I'll go into like a bit more detail. And then this will also kind of, you can blame my history for the specific examples that I'm going to give you. But yeah, so when I was in undergrad and like honors and that stuff, I was in experimental. So I was in the lab with photonics. So in that one, we're trying to design like quantum computers out of photons, which are single particles of light. Then we moved to like RMIT, the whole group moved, and because they went into more sort of fabrication stuff, and I sort of fell into a bit more theory because I'd also done like the undergrad in chemistry, so that worked pretty nicely. So I ended up like this theory of like solid state materials and quantum chemistry, which, yeah, you're right, they're kind of the same thing. It's just extended like periodic boundary conditions or no periodic boundary conditions if you're doing chemistry. So yeah, so then computational chemistry. And then I started working here at CSIRO, and it turned out to be the perfect intersection because there's one of the first applications of quantum computers. And I'm pretty sure Amina would have gone through this, but the first application of quantum computers that was thought of by Feynman was to, if we have a big quantum system, why don't we use it to simulate other quantum systems? So running quantum chemistry algorithms that I was developing for like classical computers, and my background in like experimentally building quantum computers, let's come up with some algorithms for doing chemistry, but on the quantum computer, where you just simulate it as a controlled quantum system. So I'll be going into that a little bit more in the next lecture, which I believe is next week. For today, like I said, I'll just be going over a couple examples of what these small quantum systems that will behave like a quantum computer actually are like. So I think the first thing that I want to mention are like what is actually required of a quantum system so that it can become a quantum computer. And there was a paper done a while back, David DiVincenzo. I don't know if anyone is in CQC2T or if it even still exists, but there was one of the CQC2T workshops that he was at, and he said like, oh yeah, I wrote this paper figuring out what do we need in a system to make a quantum computer, and everybody calls it DiVincenzo's criteria, and he's just like really humble about it, like he doesn't like it. So in honor of that, I'm definitely going to call it DiVincenzo's criteria for a quantum computer. So these are his. The idea is you need a small physical system operating at a quantum level that's a two-level system. And it can scale. So you can have multiple two-level systems, as many as you would like. You need to have that such that you can initialize it so that you can set them all to be the same state. And I'm sure that this is stuff that Amina's already gone through with you. Let me know if there's something that I'm saying that you have absolutely no idea about. But like all these qubits, you can initialize to the same state, typically the 0 state. There's some way to implement like gates. So some way to change the state into another state in sort of like a discrete manner. So we can control what the state is and measure it. So you can figure out at the end, it'll collapse to be like for each qubit, either 0 or 1. You can repeat it multiple times and you can see what's the probability that it'll collapse to 0, probability it'll collapse to 1. And I did see Amina present this to you, that we need the noise to be small enough so that it doesn't interfere with most of the calculation. So yeah, so I mean, like there's only a handful of these criteria. And so there's actually a remarkable number of systems that are able to satisfy this. So I'm not going to give you the big list of all the systems. I do actually have slides that have a big list of all the systems. So if we speed through all of the sort of fun toy stuff, then I'm happy to go over them. Or if you have questions, then I'm happy to look through them. But I thought it would be more beneficial to do a bit more of a deep dive into a couple of them. So first, I just wanted to sort of show off like photonics, because I think this is maybe the most intuitive one if you've already seen circuits. Like if you're coming from quantum computation, I think this one's a bit intuitive. So maybe let me ask, has anyone seen anything like this? Like has anyone dealt with like bulk photonics or integrated photonics or like lasers where you're trying to turn it into a computer?
We got one thumbs up reaction.
Nice.
But maybe most people haven't.
Okay, yeah. Okay, yeah. So then maybe let me ask then, if you were to guess, what do you, for like a photon, like it's like light, what two-level system do you think you can get out of it? What is the property of a light that could maybe become 2 levels? Just like guess. What do people think?
All right, we'll take answers in the chat. I actually think that I might know the answer. Should I have a go? Oh, people come with something better though. Polarization. I was gonna say spin, but maybe it's the same thing. I don't know.
No, they're pretty different. So
okay.
Sorry. So for spin, you would want something that's like maybe a spin half particle, like an electron. And that one you can be either spin up or down. With a photon, it's more complicated because it's spin 1. But and it's a bit harder to control. But it's not a bad answer, to be honest. It's not a bad answer. Polarization is right. That's this figure that's on the right here. So this was, in fact, my honors project. We're designing a circuit where we produce a photon. And so, like, so if you're not familiar, like polarization, just if you have sunglasses, that'll filter out like one polarization. So I don't know if you ever like looked at a TV screen and rotated sunglasses, but like these are for the people who aren't doing physics labs, because if you do physics labs, you're definitely traumatized by that. But you know, there'll be 2 different polarizations of light, and we're able to selectively filter out and also selectively manipulate it using different lenses and different kinds of, we call them wave plates. So since light is like electromagnetic radiation, it'll have like the electric field oscillating in one direction, the magnetic field perpendicular. So the electric field could either be horizontal, in other words, like same as the horizon, assuming the light is coming towards you, or vertical, so going up and down. So these are the two polarizations that a single photon can have. And yes, that is one way that we can encode a qubit. And to do the operations, it's exactly like I said, like there's just different lenses, different sort of glass cubes that we have with mirrors, such that it'll reflect one particular polarization and the other polarization goes through. And I think the reason why this is intuitive is because it literally looks like a little circuit. Like the way, like on the top here, on the right-hand side, that is the circuit. We put like Hadamard gates. We have this thing called an amplitude damping channel. I won't get into it. It's like a noise channel. And then we have like Hadamard gates and then a CZ, control Z, which I'm not sure if Amina introduced you, but like there's an entangling gate here. And then a measurement. And then in terms of the optical, like the objects literally sitting in the lab, it's the same. Like wave plates correspond to these local rotations. I have this big complicated setup for the noise channel. And then, yeah, you entangle it by just having the two photons interact with each other, collide with each other in this partially polarized beam splitter. And then when you measure it, the photon just like hits a little detector. That thing cascades into a big electrical current, and you just measure it as a click. So we split it horizontal and vertical at the end, and we just see how many clicks do we get horizontal, how many clicks do we get vertical. So that's one way it looks like a little circuit. There's another way actually that nobody picked up on, and when we want to make these really small, we can in fact encode the qubit as a path. So in this case, this is the figure on the left. The photon can, there's two photons here. So it's two qubits, and there's 4 paths. So the qubit can either, like the top qubit, qubit 1, can be either in this top path or this like second path. And whether or not it's in one path or the other, that's the thing that can be in superposition. And that's the thing that can encode a qubit. So here's the other thing that like we want to impress is a bit weird, is that in quantum physics, like any property of the system can be the thing that is in superposition, the thing that can then encode a qubit. So even where the photon is, like the path of it, can encode the qubit. And in this case, this is just in a waveguide, so it's inside a material. We just put voltages to control like the refractive index, and that'll slow down or speed up the photon in the different paths, and that'll cause it to interfere when we rejoin the paths. So that's how we do gates. And the measurement at the end is exactly the same, but instead of splitting horizontal and vertical, we just slap an optical fiber into each of the paths and then put the exact same detectors in. And it'll click when that photon is in that path, which will collapse it to be in that particular path, when before it's in a superposition. So yeah, so I hope that this is a good illustration. And also it just looks like a little circuit. Like you can see, you literally inject this, the qubits in here, and then each of these things are gates. This is a big entangling in the middle. And so it looks exactly like a circuit. So this is more, hopefully, like an intuitive way to understand one of the ways that we can build a quantum computer, that it can look pretty much exactly like how we're describing it in an abstract sense. But this is not how most of them work. With most of them, as I sort of started with, we have this sort of big fridge or some big set of equipment sitting in a lab, and the qubits are something that sits inside that particular thing there. They don't sort of go through a circuit that you predefined. The qubits are a thing that sits there, and you have like, you know, knobs and buttons and Python drivers connected to different pieces of instruments that'll control different magnetic fields or oscillating magnetic fields or voltages or something in there. And the vast majority of them kind of look like this. You have a stationary qubit and you're just doing gates to them, and you're doing measurements as things that sort of come out of them or couple them out. So for this one, I was Okay, sorry. Before we do this, are there any questions about the photonic qubits?
So can I say it's great that you paused. Have you seen Kieran's question already? Or not
No,
yet?
so
Sorry.
yeah, because
Let me
I'm
read
doing
that
full
out for
screen.
you.
So sorry, yeah.
Sorry. So let me read out Kieran's question. So, can you duplicate a qubit, and in particular, he's talking about a photon qubit, into 2 qubits if its state, horizontal or vertical, is not known? I mean, can you split a single photon in its wave nature into 2 paths?
So okay, there's a couple questions I can tease out of there. Okay, the first one is if there's any quantum state that is unknown and you want to make a copy of it, you can't do that. There's a no cloning theorem. Basically, the idea is that in order to figure out what the state was, you have to measure it, which kind of collapses it and ruins the quantum information. And there's no way of doing quantum operations that are dependent on the state that was input without sort of breaking some of the laws of quantum mechanics. This is sort of my naive way of doing it. Like you can look up no cloning theorem and it'll step you through the maths. I think the second thing is that if you have something like polarization encoded and you want to sort of split it into a path, you absolutely can do that. And you'll end up with something that is like a qubit in terms of polarization encoding, which lives in like its own little 2-level system. Tensor product or Kronecker product, the path encoding, which is its own 2-level system. And you can think of that either as 2 qubits or a Q. Oh yeah, so you can think of it as 2 different qubits. So you've effectively got like 2 qubits out of the one. It does make the measurement more annoying, and it is difficult to engineer because like in this waveguide on the right, if you have they all have to be the same polarization. If you have different polarizations, they'll behave differently, and it makes it harder to entangle them in path. The last thing I want to say is you can also split like this path. Like imagine there's not a second photon here. It's one photon split into 4 paths. You can absolutely do that. That is called a Q-quart. And it behaves similar to 2 qubits. You can think the Hilbert space is the same size. It's like 2 to the 4. The problem is that when you measure it, it'll then collapse into one of the 4 paths. Whereas when you have 2 qubits, it can collapse, like you'll get 2 clicks. 2 photons, you get 2 clicks. And that's also better because if you have 2 photons, you can give one to someone else, this is the nature of like quantum key distribution and quantum communications. Whereas if you have 1 Q-quart, you can't split that into 2 and give it to someone else. So does that answer it? Or
I think Kieran's got a bit of a follow-up question, so go ahead.
So just one follow-up question. So how expensive is that setup splitting? And the next question is, if I split the same input photon into 2, and if I'm putting, if I measure both of them, do I get if I measure the first path, if I get if I get the horizontal polarization, if I measure the second path, also I get the horizontal polarization, or it will still be, it could be different. So my question is exactly entangled, correlated?
okay. So the first bit, how expensive is it? The one on the left is significantly cheaper. The one on the right is significantly cheaper than the one on the left, which is why that's what I was doing in my honors. Because you could buy all of these components like literally yourselves. The main difficulty, I guess, is the laser, because you need to create the photons, you need a single photon source. You need a really powerful laser for that. That's probably in the thousands, but all these other components are like tens to hundreds, which is cheap in science land. The one on the right, the one on the left, you have to fabricate this chip yourself, and it's a waveguide. I don't think anybody sells them, so there's a kind of inexpensiveness to that. You kind of need to, be working in a university or some similar fabrication lab or foundry. So there's a limit for that one. So your second question, is there a correlation if you were to do polarization photons as path? The answer is there can be, and there also cannot be. It depends how you do it. For instance, if you just take photon, you don't know the polarization, and you split it in path, no correlation. Whereas if you do something like put a polarized beam splitter, which splits it horizontal and vertical, and then you encode that into path, then there's going to be this correlation. And also, I should mention, when you generate the photons with the laser beam initially, it'll generate 2 photons. This is called spontaneous parametric down conversion, if you want to look it up. Those 2 photons will be entangled in terms of polarization and also as well as path, because they will come out at like this particular angle from the crystal. Usually what we do is we'll collect them via a fiber, and then we just use them just with polarization on the right. Whereas we'll collect them with fiber, we'll change the polarization so they both have the same polarization, and we'll use it like on the chip on the left. Does that make sense?
So looks like Kieran is happy with your answer. Thank you,
Great.
Kid. We had one other question, which is from Jamie, and she was just wondering, what is the noise channel that you mentioned before?
Yep. Okay. So yeah. So this was my honest thesis. So the idea that we had is there's this noise channel called amplitude damping. The idea with this one is that if you have the other kind of qubit, the one where you have, I'll get into this in more detail later, an excited state as the 1 and the ground state of the system is 0, possibly like spin up and spin down. Then because it's an excited state that's like 1, it really wants to like spontaneously decay down to 0 because that's the ground state. And that process will cause what we call an amplitude damping channel. Like amplitude damping is modeling this spontaneous decay, how the effect it has on the quantum state. So that's what this channel is. And then this project was just saying, if we have 2 qubits and we encode it with some information, like say quantum machine learning, we're encoding classical information in. Can we put 2 copies, like we've prepared 2 different copies. Can we put it through an amplitude damping channel, entangle them, and then recover the information back at the end? And it turns out that you can. So this is different from cloning. We don't you can't have an unknown state and make a new unknown state. This is like, I have this image I want to do machine learning on, and I encode into these qubits, and then I encode the image again into the next set of qubits, and then we entangle them, and then we can get back things from noisy channels. So the idea is, as algorithm designers, we can design ways to mitigate the intrinsic noise of these devices. Yeah, does that help, or any follow-up questions?
I think that's good. Thank you so much.
Thank you.
Yeah.
All right, and with that, we should probably keep going, I guess, because we've only got 50 minutes left. So,
yeah, this should be all right. Yeah. So that was a good transition. So this is the one that I wrote up a little script because the maths is a lot nicer for this, and you can play around. So as I mentioned, most of the platforms are, instead of it being like a particular, like a photon or something that flies through, there's something that sits in your lab. In this case, the vast majority of them have like a ground state that we call like 0 in the qubit, and then an excited state, which we call 1. So in this case, I want to look at molecular NMR. Again, this is the chemistry having a bit of an effect, but also the maths is just so much nicer than any of the other ones. So in this case, the nucleus of, like, you have some molecule or maybe even a protein or something sitting in your lab. The nuclei, if it has a spin, so that's why like hydrogen, like 13 carbon, and if you've done like NMR spectroscopy, you'll be familiar. These guys, they'll have a spin. So in this case, they will be like spin up and spin down. Sorry. Spin up or spin down. We put a magnetic field in it, which splits the 2 spins in energy. And this is creating the qubit. Then Okay, I wrote this completely wrong. It's not a radio frequency light pulse. It was in fact radio frequency magnetic field. So it's a second magnetic field that comes in, and we just oscillate that magnetic field. So it's not light. So sorry, this slide is incorrect. There's a second magnetic field that sort of oscillates, and that like lets you control it. We will absolutely go through this in more detail. So don't worry if you're kind of lost it right now. I'm just giving you the picture. So this is like much more simple. That all we have to do is model, a nuclear spin and then a magnetic field. The problem with these ones is that they've been pretty popular the last few decades. They're waning in popularity a bit because they weren't discovered to be that. There wasn't a scalability that was found because we haven't really discovered how to make sort of an arbitrary large molecule. We currently just have some really good individual molecules with a fixed number of like nuclear spins, because obviously that's how many atoms are in the molecule. And yeah, so I won't go into measurement because that one actually is a little bit more complicated, but maybe we can have a chat later if people are interested. So now I'm just going to briefly do a little bit of maths. It's mostly to get to the fun programming toy that I've built, so don't be too scared. The idea is that like so with these sorts of systems, originally with quantum computers, as you saw, there's like gates, and we think of it as gates. We think of it like there's a state, you apply a gate, it turns into another state, it stays there. Then you apply another gate, and then it turns into another state, and it stays there. But with these sorts of systems, where it's literally a spin in a magnetic field, if you've done, any undergrad physics, you'll know that that's definitely going to change continuously in time. The way we describe it for a quantum system is with the Schrödinger equation, which for the context of this talk, just think of it as there's this Hamiltonian, it's just some matrix. And it just says how this state is going to change for an infinitesimal amount of time. Like the derivative of the state, how the state changes in time, just this one matrix. We'll go into details, I think, in my next talk. But for now, just a matrix. So then I want you to think about, like, let's say that this state is just transformed into another state based on what the initial state is. So there's just put a matrix out in front. So over time, the new state is just going to be this matrix times whatever the state was at initial time. And then if we literally just substitute this into so we're just trying to make it look like this gate concept. If we substitute this back into the Schrödinger equation, we end up with this thing. It's like an operator Schrödinger equation for unitaries. Don't worry about that. But so we end up with this sort of partial differential equation. The idea is you have the derivative of this matrix over time is going to be equal to this Hamiltonian times that matrix. The main way that we like control and understand these small quantum systems in order to like design them so that they can behave as we have abstractly understood a quantum computer to behave is we solve this equation to figure out how to turn U such that this U behaves like these G's. So this is pretty much the goal of the Python notebook that we're going to play around. So let me open that now.
So for everyone, if you were slightly late arriving back before, I'll just repost in the chat. There's a link that you can use to access a notebook that we're going to have a look at together. And yeah, so I've just reposted that. And then once you open that, the first thing you need to do is click make a copy and save it into your own Google Drive. So that way you can change the code and run the code and things like that. So please make sure that you click, so follow the link and then click make a copy and copy into your own Google account, your own Google Drive. Yep.
Yeah, thank you. So I'll just share my screen again. We can see what it looks like. Excuse me. Yep. So can people see this?
So we can, but maybe if you zoom in a little bit, it might be easier for us to see.
Yeah.
There we go. That's much better.
There we go. Okay. Yeah. So just give everyone like a minute or so to open it up. Yeah. So this is pretty much what I was saying, that we want to. Yep. So we want to start with just like the thing that's sitting in your lab, and you're doing. So it has its own Hamiltonian. You're doing stuff to it, which changes the Hamiltonian. And you're controlling the Hamiltonian of this controlled quantum system that just sits in your lab. We now want to.
So just to check, does that mean that we're saying that a gate is kind of like controlling the Hamiltonian in a way?
Yep, that is exactly right.
Okay, cool.
Yep. Yeah. So yeah, so in physics and like when you're in the lab for these sorts of systems, it's all like a continuous process. But we want to control it so that it looks discrete, and then all us algorithm people can take over, and we don't have to worry about all the continuous stuff getting in the way. All the theorems rely on it being like discrete gates.
Karim, are you able to go into a little bit more detail on the Hamiltonian, please? I've always struggled with that concept.
Yeah, okay, yeah. I'll be honest, I think this would make a lot more sense to you when we do the next lecture next week. Because no, it's fine. Because in that one, I'll sort of go over how we do Hamiltonians in like chemistry for stuff moving around in space, which is how we usually introduce it. For this one, I think you could think of it like the Hamiltonian gives you well, like the terms in the Hamiltonian will be like the energy of the system. And sorry.
That's okay.
Yeah.
It sounds like it's not a super intuitive concept. My basic understanding is also that the Hamiltonian tells you the energy of a particular state, and like all the components of the energy, there might be kinetic energy or chemical energy or something else. They all kind of contribute to the Hamiltonian. What were you gonna say, Ryan? Oh, sorry. Are you gonna say something, Rue?
No, all good.
Okay, cool. Yeah.
Thanks, guys.
Yeah, I mean, I wasn't sure about saying it. It's a bit abstract, but like it's like Hamiltonian dynamics. We kind of build it's like a closed system. There's no energy, there's no energy leaving or coming into the system. And so that's why the energy is like conserved through the whole thing. So that's why this is the important one, because it'll tell you how the energy is transferred over time between different bits of the system. So yeah, kinetic and potential is like the one that would be intuitive, and that's the one I'm telling you in the next lecture. So in this case, it's just like different spins. Yep.
Thank you.
Okay. Yeah, thanks. Okay, so I'll keep going then. So I think in this case, I think it's the important part is that like the Hamiltonian, it's a Hermitian matrix, and it's a Hermitian matrix over like a bunch of spins, which means you can always decompose it into Pauli matrices. So every Hamiltonian like on spins is just gonna look like this, where there's some coefficients and then just like some Pauli matrices over that many spins. So Yeah, I think Amina probably would have gone over these with you. But let me know if you need me to explain more. And then this bit you can look up if you want, but basically I just solve this operator Schrodinger equation using this thing called Crank-Nicholson. It's just like discrete time steps. It's just like you probably would have done like Newton's method or something. Crank-Nicholson is just a little bit more stable. But basically, it's just a solution that we can start with an initial u, which we start as the identity. We'll have h defined for each time step. And then we just plugged it directly into this, and it'll give us the new u at the next time step. So that's all this code is doing. Yep, so I'll just step you through it. So yeah, importing a bunch of stuff. This is code. It'll plot the block vector. So it'll make it, which I think Amina also went through with you, the qubit on the block sphere. I did just steal it. It's incredibly fickle. I found sometimes when I run it, the entire notebook crashes. So, but you get a cool animation. So there's sort of the I don't know, monkey's paw about getting that. So let's just run this. Yeah, so we'll be using it sparingly, but feel free to use it and then just refresh. Yep, so here I'm just defining the Pauli matrices. So hopefully you're familiar with this. Again, let me know if there's people need me to explain it. Yep. And then I've just done a shorthand here, but that's the same definition. And here's the identity matrix. Okay, so first, just defining a Hamiltonian. It's not going to change in time, so it's just like a constant matrix here. Then in order to do Crank-Nicholson, you just got to give it like what's the time difference between the steps and then how many steps you use. I've just set h bar to 1 because I'm lazy, but if you want to do something useful, then you would probably want to make this like useful units so that you're working in seconds. Then the Hamiltonian over time, like I said, it's just going to be this matrix defined here. And this code just makes it into an array for each time step. So this is just a big array. We start with the initial condition it's the identity. And this is literally the equation that I just put up there. So this should be very straightforward. Then we'll end up with a big array of all of the ways that the state transforms in time. These are the unitaries, like the matrix that'll transform the state over time. So then we have to multiply that by the initial state that we put in. So I start with a 0 state. And then this final state is this, all the matrices at each time multiplied by this initial state. So I run that. Oops, I didn't run this. There we go. Should take like no time at all. And then so these states, they'll be like, alpha 0 plus beta 1. And again, I'm hoping Amina went over this. Like it'll be just some arbitrary qubit state. Then at the end, I want to do like a measurement. So I'm taking the states, S, getting the first term, which is alpha, doing the absolute value squared, which if you remember, that's the probability of measuring 0. So like equivalently in the photon one, it's like, it goes horizontal and then it clicks. What's the probability that it clicks horizontal, that it clicks 0? And then this one, the 1, is just because this will be like, it's like a column vector. So this is the beta. Yeah, whatever. So, yeah. So this is what you should get because can someone answer this question? The Hamiltonian is set to the identity. What does this mean? What has it done to the state?
Once again, we might want people to post in the chat for this one. So if the Hamiltonian is the identity, what does it do to the state? Is the question. So, so got a couple of people posting in the chat that nothing is happening, and that seems to be pretty consistent with the plot here. So,
yep, exactly. So the idea is like, yeah, the Hamiltonian is the identity. Then like absolutely nothing happens. So it leaves the state exactly the same as it was. So let's make something interesting happen. So change the Hamiltonian to X or Y. So maybe I'll give you guys like a couple seconds to try it yourself.
So if I'm up to the correct part of the notebook, which I'm honestly not 100% certain, I got an error. Module matplotlib has no attribute plot in the Hamiltonians that change in time pulses section. So that was the third cell in that section. Is that where I'm meant to be up to, or am I confused?
Oh, right. Hold on. Yeah. Sorry. Yeah. You've skipped ahead, and I think that's.
Oh, sorry. I thought that's what
my bad.
we're doing now. Sorry.
Yeah.
Okay. That's all
change
right.
this cell to dot pie plot. So this was me. So the cell just before it, that's where it animates the block sphere. I was trying to fix it by re-importing matplotlib. There's a typo there, but also that's. Yeah. Just don't run this cell.
Oh, okay. So yeah. I ran that cell because I wanted to see the animation, but then it occurred to me that nothing will happen anyway. But basically, if I've run that cell, just go to the top of the notebook and start again. Is that restart the kernel and start again? Is that
yeah, restart the kernel, I think, is the safest way. I mean, I'll just show everybody. So it's like, yeah, I'm happy to take the hit on the animations. Yeah, this is also the one that'll take a while. But yeah, so yep, whole lot of nothing. So hopefully you're familiar with a block sphere. So we start at the 0, which is at the top on the Z axis, and then it continues to be 0. Yeah.
So which cell did you want us to run now?
No, I was just saying, like, let's change the Hamiltonian to X or Y. So, like, do it ourselves.
Oh, sorry. I thought that you would have implemented that for us earlier. Okay, my bad. Sorry, I misunderstood. I thought you wanted me to scroll further down.
No, that's fine. Like, yeah. Okay, yeah. I'll step you through this one because it's like the first one. So let's just change it to X here. So ham is X. Yep. So now if we plot it, ooh, something happening. So this one, let's do this. This one I'll show you the animation for because this will be more interesting. But yeah, so can people tell me, like, while we're waiting for that, what do they think is happening here? Yeah. Does anyone want some answers?
So this once again, people can post in the chat what they think is happening. I think, to be honest, this is quite complicated. I can clearly see it's sinusoidal, and maybe it's rotating around an axis, but I'm not sure which one. Because I tried it with X, Y, and Z, and I get the same plot. And I would have thought that if I did it with Z, that it might not have any change or something like this if I started in the 0 state.
Oh, really?
So, well, I don't know. Doesn't the Z gate just rotate you around the block sphere? Like, I mean, maybe I don't understand.
Yeah, hold on me.
Oh, so you're saying I should
try Z, but
that if I did Z.
Yeah, that's not surprising. But okay, so for X and Y, did anyone say anything? Yeah, Robbie flop. Robbie flop's gonna be a bit later, but yeah. Yeah. So it goes from 0 to 1 and back to 0, and we can see it here. So with X, it's rotating around this X-axis. When you're looking at the this 0 and 1, remember that we're measuring on the Z-axis. So we're seeing it like bounce up and down sinusoidally because it's actually rotating like a circle on the block sphere. So yeah, now I want to try your Z one because that should be not the case.
I tried it again,
Yeah.
and the Z now is flatlining. Sorry. I don't know. I must have made a mistake the first time.
No, that's fine. Yeah, always good to double check. So why don't you explain? If it's rotating around the Z-axis, then why do we see anything here?
So if you're already at the top, at the 0 state, then it doesn't really matter if you apply the Z. It doesn't look any different on the block sphere, and it doesn't change your probability of measuring 0 or 1.
Yeah, exactly. It doesn't change the probability because you'd be sitting at the top. Was this in the right place? So you'd just be sitting up here, rotating. It is technically rotating, but then that rotation, you can't measure it. And it has no effect on like any of the subject. It's just like imagine the arrow pointing at the top and just rotating like this. So, I mean, just because you asked that question, what do you think is going to happen if we input a plus state? There'll be a question later that's that, but I'm happy to skip ahead. So, are you all familiar with like the plus state?
So if you started on the plus state and then applied a Z Hamiltonian, is that what you're saying?
Yep.
I guess you'll rotate around the equator would be my guess.
Yeah.
So you'll be stuck on a 50-50 on that graph. It'll just look like you're staying on the 0.5,
Yeah.
but at least you'll see it in the animation.
Yeah, there's some numerical error here, but this should actually be flat. Yeah. Both of them 50-50 at 0. Yeah, that's exactly right. Yep. See? Yep. So there you go. So I think the big thing that yeah, I changed DT or numt. So that's more like yeah, feel free to play around with that. That's just sort of showing you that there's this defines like a total time for the simulation. So if you let it go infinitely, it would just oscillate infinitely, but you can also zoom in or get better precision, or if this is not precise enough, then this equation breaks down. So these are the nice numbers that I've found converges nicely. So yep. And then oh yeah, okay, let's do this. So if we have to do, sorry, yeah, if you re-input the matplotlib as PLT, that fixes the things that this breaks, except it then refuses to save properly ever again, but that should be no problem. Okay, let's try. So with X, if you remember, we get rotates around the X-axis. Oh, need to make this a 0 state. And it looks like this. If you make it Y, it'll rotate around the Y-axis. But it looks exactly the same. So I think that's too tricky of a question for you guys right now. But I think the important takeaway is that they both don't, like, they both look exactly the same. And I think it's also important that because when you're measuring it, when you're just looking at how many collapse to 0 and how many collapse to 1, you're collapsing that block sphere just along the z-axis. So your measurements aren't really affected by if you're rotating x or y. But the cool thing is when you rotate, like, we have the whole block sphere, like, not in measurements, but in terms of, like, just to play around in. And when you measure it, it just collapses down to the z-axis. So that's sort of where a lot of the quantum algorithms sit, is that the advantage comes from the fact that we get this whole sphere to play around in. And the limitation is that when we're measuring it, it just collapses back to the middle. So we have these extra degrees of freedom, but only, like, while we're running the quantum computer. And yeah, anyway, to finalize it, I think the main takeaway is that, look, the Hamiltonian, it's just some matrix composed of these Paulis. Each of these Paulis, all they do is rotate it along that axis of block sphere. With yeah, so now we can have a look at the pulses, and this is asking, like, can we use these to then control the state? And the idea is that instead of it being a fixed Hamiltonian, like we're fixed for, like, all time, we can sort of turn off and on the Hamiltonians. So with pulses, I just read, like, a really basic function. The idea is there's just a square pulse. It literally turns off and then it turns on again. So, and it occurs at some point t with some width. Although I've done it like this, where I did, like, t minus t0, where that's the center. So here I have 2 pulses implementing 2 different Hamiltonians. Here I've just done 2 y rotations. I've done it at, like, 0 and then 2 time, and they're just 1 wide. So let's run it. Didn't run this one. So now I'm just going to plot what the pulse looks like. Oh, that's weird. I should make them further apart. Sorry. Maybe do this. Yep, so you just got, like, 2 pulses. So the idea is that this y Hamiltonian only exists for some amount of time. So the y Hamiltonian is turned on here. Then there's no Hamiltonian, which is the identity, which we saw does nothing. And then the y Hamiltonian comes back here, and there's nothing. So let's see what it does to this. All right. So let me just get a comparison. Yeah, it's already here. So so remember, when the y Hamiltonian is turned on, it looks like this. It's rotating around the y-axis. Now we have these 2 pulses. Can somebody tell me what's happening here?
Once again, we might call for people to post in the chat what's happening here. This is a little bit complicated, so if you don't know, I think that is okay. I'm not fully sure if I fully understand what's happening here either. So
okay, I'm plotting them on top of each other, which is okay. It's still confusing, but yeah, this one will be a bit tricky, but
so maybe I'll someone say that 2 different Hamiltonians are acting on the pulse.
So yeah, so here I've just set them both to be y. So but you could give it as the Hamiltonian switches between y here when the pulse is on, and the identity here when the pulse is off, C0 here, and then back to y, and then back to 0. So maybe I'll just do 1 pulse, just to make it a bit easier to understand. So now, or maybe I do the pulse in the middle. I'll just do 1 pulse here, in the middle, And let's have a look at what this looks like. Let's have a look at this one now. So what's happening before the pulse is switched on? Can someone answer that?
I mean, I don't know if I should try and answer for the group here, but yeah, everybody's saying it's flat. It looks like we're applying the identity as our Hamiltonian, and nothing's happening.
That's exactly right. So nothing happens when you have the pulse off. You turn the pulse on, which makes the Hamiltonian be like Y. Then what's happening while the pulse is on?
So once again, I'll let people post in the chat, but I'd say to me, it looks like we have the phenomenon that we were observing before, where the Hamiltonian was set to Y, and we just have, I like the way that some people have said it, is that we're now rotating around the Y-axis. So
Yep, that's exactly right. And then what happens when it gets switched off again?
looks like we go back to the identity gate again. So
Yeah, but what do you notice about the probabilities of 0 and 1 now?
So they're not necessarily where we started at 0 and 1. They could be somewhere else. Sorry, I feel like I should give more people more time to post in the chat here. But I can verbally speak a little bit faster than people can type. So if anybody has better, more detailed observations, Kieran's got one. So state remains at the point where it's switched off. Probability is not zero for both.
Yep, that is exactly right. So I think the big thing here that you should get is that when you turn off these bits of the Hamiltonian, you're just left with like the identity in the Hamiltonian. It means that nothing is changing, but it doesn't mean that nothing like has changed. Whatever you've changed beforehand gets stuck that way. Sorry. So yeah, so the whole point of this one is that, like, how do you design a gate that's like a discrete operation that goes from one state to another? This is in fact exactly how we think of it, that there will be the control of the Hamiltonian. We switch it on, all the states change, but when we switch it off, they stay exactly where they were at the end of that pulse, which means if we can control what's happening with these pulse, we can control what these states transform into, and then like fix the amount of time in the pulse, or fix all the experimental details of the pulse. To be honest, they do it experimentally, so they'll just sweep parameters until they find everything works the way it should. Then they'll just leave it alone. That pulse becomes like, this is now the gate that transforms you from this state to this state. So this is the one that would also be nice to do animation for. So let's have a look. Yeah. Yeah, so we'll see what it looks like on the block sphere, and then I'll like, there we go. So it stays the same. Pulse goes on, pulse turns off. See, pulse turns on, pulse turns off. So then you can think of it as, this is a gate that turns you from like a 0 state to whatever state that is. And it works like this sort of discrete operation, just like a gate. And then when we want to, like the gates that are necessary for quantum computation, we just solve for particular like characteristics of the Hamiltonian, or control variables of the Hamiltonian, such that they implement the operations on the qubits that we want. So that's sort of the big takeaway that I want you to get from this. And like in the next like 10 minutes, yeah, whatever, however long we have left.
Just
I'll
a tiny
go-
bit more than 10. So, yep.
Okay, yeah, that's fine then. Yeah, so then we can go over, like, I'll just show you what some realistic Hamiltonians for this molecular system look like. And then you can get a feeling for what are the actual knobs that we turn, what are the wires going into the cryostat, that sort of thing. Such that we do literally this exact thing. This is the exact principle that all of these kinds of quantum computers rely on. The ones that are like pulse controlled. Okay, so do we have any questions before we continue with some realistic Hamiltonians?
So we've got a couple of questions in the chat here. So we'll start with Samuel. So Samuel said, is there any loss when you keep the state? And then had a follow-up comment. So you're using the pulse for state control.
Yep. So I haven't gone into the noise at all. So obviously, experimentally, there's always going to be noise. At minimum, we don't have, infinitesimal control over the time. It'll be like, I don't know if you know, but there'll be like, a little ADC or something, or maybe there's this thing called like a pulse blaster card. It's kind of like a GPU, but for pulses. And so that thing will have a specific like rate that it can change the pulse for, and it'll have hardware parameters. So we don't have infinite control over this pulse, firstly. So there's a precision error. Secondly, there's also natural noise channels. So I already brought up before amplitude damping, and that's the one which I'll get into when we look at the realistic Hamiltonians. If it's like an excited state, it'll want to spontaneously decay to the ground state. So if you're just keeping the state exactly the same, there will be some spontaneous decay for these kinds of quantum computers where it's an excited state. Yep.
And then we also, sorry. Go.
Sorry, Lachlan. I was like saying that it kind of feels like I study aerospace, so it feels like stability and control, where the damping of the occurs, and then there's some losses as well. So, but it's interesting because it also links to music and synthesizers, which is like you use LFO, and so you kind of you can control the notes by the LFO you're using. So it's interesting how you can do that with these kind of circuits. Yeah.
Yeah, that's all exactly right. Like, it's a lot of like control engineering and exactly like signal processing people. They all work on this stuff. All the electrical engineers. Yeah. That's great.
And then Kieran's also asked a question, which I think is clarifying something that I was thinking of too. So I've been mostly trying to keep my camera off because my internet's really struggling at the moment. But so whenever we're applying a Pauli gate, we're actually just controlling the duration that we of a continuous gate. Is that true?
Yeah. So, I mean, it's more like, I like to think of it as the concept of quantum computing is like an abstraction. I mean, the same way computing itself is an abstraction of the electrons doing stuff, in this little box we're all looking at. And so when we're working at this sort of hardware level and the physics of it, it's more like, what is the actual thing doing? And how do we make the thing look like the thing that we want it to look like? So then we can use all of these maths and theorems to actually do something useful with it. So I don't know if that helped or if that was a bit too abstract an answer, but
I think that it does clarify things. And then Kieran has also written then that so there's no two gates producing the X gate will ever be exactly identical, as kind of like a side remark. Is that true?
Philosophically, probably not. But like, in our modeling, they'll be identical to within like precision or within error. So from our, physics measurement point of view, we would consider them, we would have like a natural threshold to consider two things identical, that we wouldn't worry about it.
And if we go back, I mean, this is me adding a bit extra onto the question, but if we go back to the example we were talking about before with photonics, then basically it seems to me like the width of whatever's changing the polarization, like I assume if you have some sort of what do they call them? Are they wave plates? The ones that rotate the light around. So I assume that how much time you spend in that is essentially equivalent to determining how long the Hamiltonian is applied to the photon.
Yeah, I mean, so you can think of everything as having a Hamiltonian. The gates one, the wave plate's nice because it's literally the rotation angle. So you literally just set it to be whatever angle you want, and it's sorry, it'll preferentially rotate, like the horizontal and vertical axis will be preferentially like offset by enough to do that particular angle. Sorry, I'm just coming off a cold, so I'm a bit sorry, I saw another question. Okay, so the anharmonicity, that's more an issue for with the superconducting qubits. They're not really a two-level system. With superconducting qubits, you have like an anharmonic, like like a harmonic oscillator. It's like whoop, a parabola, and then you have like states in it. Superconducting qubits are an anharmonic oscillator, so there'll be an extra third, like there'll be like 0, 1, and then 2, but 2 is really high in energy. But sometimes if things are kind of, there's always a chance that it'll leak from the 1 up to 2. So that's what they say by anharmonicity. Okay, thank you. Okay, let me maybe spend like, I think, 5 minutes or something. I just want to show people what it
we got 5
like.
minutes left. Yep.
Yeah.
Yep.
So I mean, if you know like spin in a magnetic field, the interaction terms literally like the magnetic like dipole and the magnetic field. This is the energy. That's literally the term you slap in there. And then it'll be whatever the direction of the spin, like the dot product of the direction of the spin and the direction of the magnetic field. So let's assume it's in the Z direction. So the Hamiltonian literally just looks like this: strength of the magnetic field, the gyromagnetic ratio, and then just a Pauli Z. So this is the bit where I was going to say do the plus thing. So we've already done that, so that's great. So if you have the static magnetic field that creates the splitting between the two spin states, spin up and spin down, or spin aligned with the field and spin anti-aligned with the field, your Hamiltonian is this rotation around the Z-axis. So then when we want to add a control to this. So that just sets up the qubit. And it sets up rotating around the Z-axis, which doesn't change measurement at all, because you always measure on the Z-axis. So that's the important part. It doesn't change the measurement, but it sets up the qubit and it lets it spin. To do the control, we have an RF pulse. This radio frequency pulse is literally just another magnetic field, but it oscillates. So let's put it in the X direction. It could also be Y. So it could be perpendicular to, it's just perpendicular in some way. The term looks like this now. So this is our pulse envelope, which was a square pulse from before, just switching on and off. It's literally the same coefficients, but now we oscillate it. So it has a radio frequency oscillation up and down with some frequency and some phase. And this applies in X. So we can see this already literally looks like the simple example I gave earlier, where we can control a pulse that will control in the X direction. So we can control exactly that it rotates in X, stops, rotates in X, stops, and then it's also automatically rotating in Z. So you can use those two to actually just do universal gates. It's a bit complicated to see here, but I'm hoping that this is pretty illustrative. I then did a little bit more maths of just like, so what we do in physics, we throw out half the terms. And we also move into the rotating frame, as in like, we're just looking at it from the perspective of, since it's sort of always rotating at the same frequency, that initial static magnetic field term, we're sort of going with it, like sitting on a roundabout. And when we do that, then we can see that it ends up, the whole Hamiltonian just looks like this. So there's a pulse, and you have your radio frequency magnetic field, and you end up with a cosine x and then a sine with y. And so then you can control the whole Hamiltonian with this phase of your like radio frequency pulse. Because if this phase is 0, you end up with x, and if the phase is like pi odd 2, you end up with y. Sorry. So yeah, and then this delta is this detuning, which is how different this radio frequency is from the quote unquote frequency of the static term, which is just like gamma, the gyro magnetic ratio and the magnetic field. So look, that all seems pretty complicated. I think the ultimate takeaway is that this is what an actual Hamiltonian looks like when we're controlling the thing with just like a magnetic coil that's oscillating at some frequency. We could use the difference in that of the interaction strength between the coil and the static magnetic field that created the qubit to control this term. And we could use the phase of that coil to control whether we do an X rotation or a Y rotation. So yeah, I mean, feel free to maybe have a look at some of these questions, have a look at some of this stuff in your own time. I'm happy to answer like any questions over email as well if you are interested and want to learn a bit more. But yeah, do you have any questions now in sort of the last couple minutes?
Can I just say?
Hi, sorry, could you please say that?
Yeah.
Oh, hi. Sorry, there was a bit of lag there. Sorry, I just.
If anybody needs to leave now,
Hello.
then feel free to go. Thank you so much, Akib, for today. And then if people want to stay back and ask questions, that's fine. But we don't want to hold people past the finish time. So thank you. Can we just all say a big thank you to Akib? And then if anybody would like to stay back to ask questions, yep, we can do that. Thank you.
Okay, yeah. Hi, Jamie, I think you wanted to ask something?
Hi, I put it in the chat if that's easier.
Oh,
okay.
Sorry, Jamie. I didn't mean to interrupt you.
No, that's okay. There was some lag.
Yeah. Yeah, so the idea here is the Hamiltonian it's literally just the energy in the system. Because we're assuming everything's a closed system. So the energy is the thing that controls how it changes in time. And I'll go over in a bit more detail next lecture next week. That might be a bit easier to get your head on.
Sure. Okay, thank you so much.
Thanks. Yeah, thanks, Lachlan.
And did anybody else have any? Oh, sorry.
No, I just wanted to thank you. Like, you're very, very good host.
Oh, thank you. I've been struggling where my internet has like been dropping in and out. So I tried turning off the camera and things, and that's probably why we got that delay before. It's just that yeah, I don't know why this happens, but anyway. Yep. Though I notice we've got, I think, still another 4 people kind of around. Did anybody want to ask any other cool questions? I might stop the recording at this stage because I think that, yeah, all the major questions have been asked and it's just the last few people leaving. So